This is the second section of chapter 7, and in this section we're going to be doing the hypothesis test for the mean of a normal distribution with unknown variance. Right, so this is a test to see if the population mean has increased, decreased or changed, put a D there, based on the mean of a sample. Now in normal maths you'll do hypothesis testing on the mean, which is the same type of hypothesis testing, but you'll know the population variance, so you can just use that method in normal maths. However, since the population variance is not known, we use the t distribution to find our critical value or values if it's a two-tailed test. Then we need to convert our sample mean into a t value by using this formula here. T is equal to sample mean minus the population mean divided by our sample standard deviation over the square root of n, sample size. And then we decide if our sample mean t value is in the critical region. So it's important that we draw diagrams so we can see clearly where our critical values are and clearly if our sample mean t value is in that critical region, and that will help us decide if we accept or reject H0. Example 5. A shopkeeper sells jars of jam. The weights of the jars of jam are normally distributed with a mean of 150 grams. Let's underline that. A customer complains that the mean weight of the 8 jars she had bought was only 147 grams. An estimate for the standard deviation of the weights of the 8 jars of jam are calculated from the 8 observations was 2 grams. So you can see in this question we don't know what the population variance is. We know what the population mean is, 150. So this is where we use the t distribution to help us answer this question. So part A, test at the 5% significance level whether 140 grams is significantly less than the quoted mean. Right, so the first thing that we do in any hypothesis test is we write down H0 and H1. So H0 is going to be that the population mean hasn't changed, it's 150 grams, and H1 is going to be that the population mean or increased, decreased or changed. Now her mean was less than 147. She's complaining that the mean of the population is less, so that'll be less than 150 grams. This tells us that it's a single tail test, a lower tail test, and that area is going to be 5%. Now I have a sample size of 8, which means that my degrees of freedom is going to be 8 minus 1, 7, and it's going to be a t distribution that I use, and this t distribution will have 7 degrees of freedom, and the significance level, that's going to be 5%. We draw out our t distribution, t here, and we're going to put on here our critical value. Let's draw that a little bit better. Let's just do it in a different colour. So we've got here, that's even worse. Let's try again, see if we can get it better. There we go, something like that. So it's going to be 0 in the middle, and we're going to be using the tables to find this critical value. Now if it's a lower tail test, that means that this area here needs to be 5%. Now that means that I need to stick a negative in front of any value that I find from the table. So from the table I go down to the 7 degrees of freedom row and then go across to 5%, and I see 1.895. So 1.895. So that tells me that this value here is negative 1.895. So I'll just put down critical value equals negative 1.895. I now need to see whether basically the t value that goes with this sample mean value is in this critical region. So this is where I use this formula: t is equal to sample mean minus the population mean divided by s over the square root of n. So t will be equal to, now my sample mean, or her sample mean, was 147. The population mean was 150 divided by, now the sample, now what's its sample variance? Oh, that's standard deviation, so do watch out for that in case we need to square root that. So it's just 2 divided by the square root of n, and that's 8, square root of 8. So let's work that out, see what it gives us for t. Now that comes as exactly as minus 3 root 2, but I'm not really going to be able to see if that's less than the value there, my critical value. So let's change it to a decimal: minus 4.2426, and so on. Okay, so because I've done a diagram, I can clearly see that it's going to be over here. It's going to be in that critical region there, minus 4.2426. Okay, but I do need to state that. So I'll write something like, since minus 4.2426 is less than minus 1.895, it's in the critical region. So in critical region, and since they've used this word significantly, we want to talk about whether something is significant or isn't significant. Now if we accept H0, it's in the acceptance region. It's not significant, so we can forget about it. It's been no change. But it's in the critical region, it is significant. So in critical region, so result is significant, therefore we're going to reject H0. Now I don't need to make a comment on it, normally I would. We do that in part B. Part B says, discuss whether the customer has cause for complaint. And we will just write down, yes, they have cause for complaint. Have cause for complaint, as there is evidence that the population mean, or mu, is less than 150 grams. Example 6. The temperature in centigrade was measured at noon on 10 days during the month of March in West Cumbria, and these were the readings here. Use a 5% at significance level, test whether or not this is an increase over the previous year when the average noon temperature was 13.5. Right, let's start with H0. This is a full hypothesis test, and H1. So H0, it says that the average noon temperature was 13.5 Celsius. H1, we're testing to see whether it's an increase. So that's going to be that it's greater than 13.5 Celsius. So you can see here we do not know the population variance, so this is going to be using the t distribution. Now I've got 10 readings here, so n is 10. That means that our degrees of freedom is 10 minus 9, not 9, 10 minus 1, which is 9. And we're testing at the 5% significance level. It's a one-tailed test, so it's going to be 5%. So we can use that to look up our critical value. And the table tells us that that's 1.833. Now we're going to work out the sample mean and the standard deviation for the sample using our calculators. Right, so the sample mean is 14.28 and the sample variance is some long number, so I know it's going to be the square root of the sample variance, which is 2.344. That's an easier number to deal with. So now we'll work out our t-value, basically convert it into a t-value, which is going to be my sample mean, 14.28, minus the population mean, which is 13.5, or the previous year, divided by the sample standard deviation, divided by the square root of the sample size, which is 10. Let's see what that gives us for t. And that gives me a value of 1.611075, and so on. So now I'm going to draw my diagram just to make sure I'm absolutely sure whether this is in the critical region or not. So this t distribution is telling me that the critical value is 1.833. So remember that's 0 in the middle there. So here's my critical region, because remember it's an upper tail test. And 1.611, right, that's over here, isn't it? So it's not in the critical region. 1.611. So we can write down, since 1.611 is less than 1.833, it is, and there's a couple of ways we can write this. We can say it's not in the critical region, it is not significant, so I'll put down it is not in the critical region, or you could just say that it's not significant. Therefore, we accept H0, or we fail to reject H0. And then, therefore, there is insufficient evidence, or not enough evidence to suggest the mean temperature has increased. Example 7. A concrete manufacturer tests cubes of concrete at regular intervals, and their compressive strengths in newtons per square millimetre are determined. The mean value of the strengths is required to be 0.7 newtons per square millimetre. A new supplier of cement offers to supply the firm at a cheaper rate than the present supplier, and a trial bag of cement is used to make 12 concrete cubes. Upon testing, these cubes are found to have strengths of x such that the sum of x is 5.52 and the sum of x squared is 2.542. Assume that the strengths are normally distributed. Okay, and then what we need to do in part A looks like a full hypothesis test with conclusion. Stating your hypothesis clearly, test at the 5% level of significance whether or not the use of the new cement has been altered, has altered the new mean strength of the concrete. So we start with H0 and H1. Now the word altered here, rather than increased or decreased, means that H1 is going to be not equal to, and this is going to be a two-tailed test. So let's start by with our t distribution. So sample size is n, 12, degrees of freedom 12 minus 1, which is 11, and then our t distribution is going to have 11 degrees of freedom, and we're testing at 5% level of significance. Because this is a two-tail test, each tail is going to be 2.5%. Okay, so two-tail test. So now we're going to work out our sample mean and our sample variance. Our sample mean is going to be the sum of x over n. We've been given the sum of x, 5.52 over n, which is 12, and that's 0.46. And then our sample variance, so we'll make sure that we square root this. So this is the sum of x squared, and actually it's going to be an unbiased estimator that we work out. So let me write down the formula first. So 1 over n minus 1, and that's going to get times by the sum of x squared minus n times by x squared. And that's the mean squared there. Mustn't forget that little bar. Okay, so that's the formula I'm going to use to work out my unbiased estimator. So that'll be 1 over n minus 1, so that's 1 over 11, times by the sum of x squared, so I've been given that 2.542, minus n times by basically the mean squared. So n is going to be 12 times by the mean, 0.46 squared. Now that gives me an exact value of 7 over 275 over 500. Now if I press the SD button, I get some decimal number. It looks like it's recurring 5454, so it looks like 2.54 recurring times 10 to the power of negative 4. So I think I'm going to be using that exact value in my calculation. So now we'll work out our t value, and that's going to be equal to our mean, 0.46, our sample mean, minus the population mean, 0.47, divided by s, now that's going to be the square root of this, divided by the square root of 12. So I'll tell you what, that's going to be a nasty looking fraction, so I'll write it as a division rather than a fraction. So 0.46 minus 0.47 divided by, and this will be the square root of 7 over 27,500 divided by the square root of n, which is 12. Let's see what that gives us for t. Right, so I get minus 2.17124 and so on. So here comes my diagram, my t distribution with 0 in the middle, and my critical values, which I haven't looked up yet, but I have worked out my actual value, and that's going to be minus 2.17. So if I go back to this part here and work out my critical values from the table, so 11 degrees of freedom, 2.5%, and I get 2.201. So it's going to be plus and minus 2.201. So we'll mark those in. So 2.201 and the negative 2.201. Right, that's going to be over here. That 2.201, which means that that negative 2.17 is not in the critical region. So our conclusion is that since minus 2.171 here is greater than minus 2.201, we accept H0, or you can say that it's not significant. There is not enough evidence to suggest the mean has altered or changed. And then lastly, part B, in light of your conclusion to the test in part A, what would you recommend the manufacturer to do? I would say, well, since the mean strength is not significantly different, we saw that with this hypothesis test, they should just go with a cheaper product. You know, there's not much difference in terms of the mean strength of them, and to save money, go with a cheaper one. So you should now be able to do exercise 7B on pages 173 to 174 of the textbook.